Welcome everyone. Today we're going to be evaluating quite a terrible looking sum. As you can see, the sum is infinite and the cosine function is one of its sum ends, where the cosine of theta in this case is 1/5. If you expand it, it clearly does not look that friendly. But if we remember one of the fundamental results of complex analysis, this sum, as you're about to see, is actually extremely simple. And what is this result of complex analysis am I talking about? How do complex numbers even relate to anything for the cosine of n theta? Well, it could be none other than Euler's identity, which states that e to the power of I theta equals to cosine of theta plus I sine of theta, where e is Euler's number and I is the imaginary unit. And so, relatedly, if we raise this form of a complex number to the nth power, we get that e to the I theta to the power of n is equal to e to the I n theta by properties of exponents, which you can see is the cosine of n theta plus I sine of n theta. And so the real part of this expression, e to the I n theta, is equal to cosine of n theta, which is exactly what we have in our sum. So let's define a new sum, the value of which we will call s, which is going to be also from 0 to infinity. But here we're going to substitute the cosine of n theta for e to the I n theta. And watch what will happen. We substitute that in, e to the I n theta over 2 to the n still, as we have here. And then we can take out the n, and to get e to the I theta over 2 all to the power of n. As you can see, this is a geometric series, which we can simply resolve, and we know that it converges because for all values of theta, e to the I theta over 2 will be less than 1. And so, but we're not done yet, because we'll still have an unnecessary imaginary component in s. And so to evaluate our sum, where we don't need an imaginary component, we're just going to find this s and then take the real part of it. Hopefully this makes sense. So now we can use our formula for the sum of an infinite geometric series, which we know converges, and that is going to be the first term over 1 minus the common ratio. I should not explain here, 1 is the first term because this is raised to the power of 0, and the common ratio is whatever inside these parentheses. Alright, so this is what s is equal to, and now we can expand e to the I theta using Euler's identity, and then get to 1 over 1 minus 1/2 the cosine of theta, minus 1/2 I sine of theta. I just used Euler's identity and then distributed this 1/2 everywhere. So, alright, that is what s is equal to. We also have a value for cosine. So can we just substitute this in? Well, remember, it won't be that much use to us because we want to find the real part of s. And in order to do that, we have to simplify this denominator to not contain any imaginary component. So we want the imaginary component in the numerator, because then we can split it into fractions, take the real part of s, and actually evaluate our sum, which we had from the beginning. And so let's still clean this up a bit to remove this I in the denominator. And we can do that by multiplying this whole thing by its conjugate, multiplying both the numerator and the denominator by it. So the conjugate of this will be 1 minus 1/2 the cosine of theta plus the half of I sine of theta. It's the same thing, just with a switch sign on the imaginary component. And so the reason for doing this now is because we have a difference of squares. We have the number and its conjugate multiplied together. That's going to be a difference of squares. And so we can write out the square of the real part, 1 minus 1/2 cosine of theta squared, difference with the imaginary part squared. And the reason for doing this is quite obvious, because when we have an imaginary part squared, the I squared becomes -1, and that just gets cancelled. And so s is going to be equal to all of this. I'm going to write it here. All of this, 1 minus 1/2 the cosine of theta plus the half I sine of theta, and then over these squares, 1 minus 1/2 the cosine squared, and then this is going to be plus, because we have an I squared, which is equal to -1, 1/2 the sine squared of theta. Alright, and that is equal to s, and then to find the real part of s is very simple because we can just cut out this imaginary part right here because our denominator is completely real now. So now we can continue to evaluate in our sum by taking the real part of this fraction, and we can do that because we know the value of cosine of theta and sine squared of theta we can also find. So the real part of s, let's just look at this and substitute 1/5 everywhere we see the cosine of theta. It's going to equal 1 minus 1/2 times 1/5. All right, then it's going to be 1 minus 1/2 times 1/5, all quantities squared. And then sine squared of theta, well, we can easily derive that. Remember the Pythagorean identity that the cosine squared plus the sine squared is equal to 1. And therefore, the sine squared of theta is going to equal 1 minus the cosine of theta squared, right? And this is going to equal, because cosine of theta is 1/5, 1 minus 1/25. And so we can add that here, plus 1/2 times 1 minus 1/25 right here. All right, so now we have an actual numerical answer for us. It is right here. It's a bunch of fractions. And I'll just tell you to skip the evaluating part of this because this is our answer right here. You can leave it unsimplified. But simplified, it is really quite a nice number, which is 6/7. And so that is the answer to our sum from the beginning. This converges into 6/7. And yeah, that is the whole trick I want to show you for today's video, using Euler's identity in order to get an expression for the cosine of n times some angle, and then using the real part to evaluate this. And yeah, thank you all for watching to the end. Please make sure to check out my other videos and leave a like and subscribe if you enjoyed. So thank you for watching. I'll see you in the next one.